Welcome, class, to our first part of our transmission internals. And this will be going over gears and gear ratios. This is important to understand the different type of gears and the gear ratio, how we get gear ratios in an automatic transmission, and how that gives us our different speeds of our automatic transmission. So our objectives in this lesson is we're going to talk about our various gear types that we might find in automatic transmissions in one form or another, the effect that these gear types and gear ratios have on speed, torque, and direction of rotation. And then we're going to explain gear ratios and the effect on vehicle operation. Types of gears, we'll kind of list these out, and then go through each individual gear. We have spur gears, helical cut gears, bevel gears, spiral bevel gears, hypoid gears, worm gears, these used in like speed sensor drives or in non-electronic transmissions where we actually have a cable, speedometer cable that connects from the transmission up to the speedometer gauge in the dash. The two gears that mesh together sometimes will be like this to drive our speedometer so we know how fast we're going. And then the most common type to give us transmit power through a transmission are our planetary gear sets. Spur gears, these are common in a lot of your older manual transmissions. You'll still see it maybe in some manual transmissions today. Could be seen in some different gear sets in an automatic transmission, older automatics. But for the most part, we don't use spur gears in an automatic transmission today. But the gears cut parallel to the shaft. So as you can see, they're in straight line with the shaft. And produces a straight pressure between the driving and the driven gear. Now we have a helical gear. As you can see, the teeth of the gear are not parallel like a spur gear, but they're actually at an angle. This is the most common gear used in transmissions like your manual transmissions, where we have two gears meshing together. And this can be used in automatic transmissions, like in our transfer gears, especially in transaxles, where they're transferring where the input power comes in and we're transferring it over to, say, the final drive or the differential of your transaxles. You might see spiral cut gears, pinion gears, and sun gears in an automatic transmission. In our planetary gear sets, they will have helical cut gears like this. Next gears we're talking about are bevel gears. These are most commonly found in our differentials. If you remember, in a rear-wheel drive transmission, we don't have a differential in our transmission. We have a separate differential, and then we connect the transmission to the differential through a drive shaft. They're called bevel because, as you can see, that the inside of the gear is at a different angle than the outside. It seems like it starts small and it goes big on the gear. And most commonly, these bevel gears on two separate axles. As you can see, you'd have a vertical axis on, say, the purple gear and a horizontal axis or axle coming through on the blue gear. These are pretty common, what we call bevel gears. We can have spiral cut bevel gears that are make up like this, but the way the teeth are set, their teeth are cut in there like a helical gear set, where the teeth come in at an angle, but with them still being on separate axis and kind of coming out of a bevel, where it's the gear kind of starts small and gets bigger. That would be a spiral cut type of bevel gear. A hypoid gear set, this is what we find in differentials, where you have a pinion gear and a ring gear. The pinion gear is power that's coming in. Again, the only time we'd see something like this would be in a differential, in a transaxle. It wouldn't necessarily look exactly like this, but there are some transaxles where it'll have a pinion and a ring gear. A lot of your transaxles, there's just an input that comes into the gear set, and it doesn't necessarily have a ring gear. But this is what would be a hypoid gear set. And then a worm gear, this is where we got, again, gears on angled shafts or separate shafts. The lower gear would have a shaft that would be like if you were looking at it and the shaft was coming to us. That would be like the output shaft of a transmission, where there's gear going across. Then it meshes in there, and that'll be used, say, to drive a speed sensor or drive a shaft that drives a speedometer cable. That would be a type of a worm gear that you might find in an automatic transmission. And then a planetary gear set. These are the gears that we find in a transmission in most automatic transmissions. And we'll talk about planetary gear sets in the next lesson. But this is how we get our different speeds of our transmission. This is the most common type of gear set that you're going to find in an automatic transmission. It consists of 3 separate units, to where we have a sun gear, a planet pinion or planet carrier with gears in it, and then a ring gear. The planet pinion or planet carrier gears connect the sun gear to the ring gear. And when we get into planetary gear sets, we'll explain how these operate and how we get different gear speeds out of a planetary gear set. Now we're going to talk about gear ratios. We hear, if you're around automotive anytime, you're going to hear about gear ratios, whether rear differential gear ratios, whether we're talking transmission gear ratios. These gear ratios are how we get the different speeds of a transmission, and how we determine say the RPM of an engine as it runs down the highway. Do we have a high gear, low gear? And we'll talk about what that means and what it means to the operation of the vehicle. A gear ratio includes a driven gear and a drive gear. Okay, the drive gear is obviously the gear where the power is coming through. Okay, it's the source of the engine torque and rotation. Where the driven gear is rotated by the drive gear. So that would be like your output device. So if the input is the drive gear, the driven gear is the output. Okay, and we can determine this gear ratio by dividing the number of teeth on the driven gear by the number of teeth on the drive gear. Okay, and I'll kind of show you how we do that here in a minute. But it's important to understand the difference between the driven gear and the drive gear. Drive gear is your input, your source of power, and your driven gear is your output, where it's transmitting the torque either to the drive wheels or to another part of the transmission. Gear reduction, this is when we're talking about gear reduction. Again, we'll talk about how we figure gear ratios here in a minute. But gear reduction is when the drive gear moves faster than the driven gear. This is where also the drive gear is smaller than the driven gear. That's when we get gear reduction. This results in an increase of torque, but a reduced speed. That's why a vehicle with low gears in it, a low gear ratio, has the ability to multiply torque. In other words, we could take a vehicle with a low gear ratio and pull a much larger load than a vehicle with a high gear ratio. But we could not go as fast. That's why we get our different speeds of our transmission. We have lower gear ratios, which means more gear reduction at low speeds. And as the transmission shifts, we start getting a higher gear ratio or less gear reduction. Okay. A real easy way to remember that: the higher the ratio number, the lower the gear. Okay. In other words, more gear reduction that we have. Okay, now we're going to talk about torque reduction, where the driven gear moves faster than the drive gear. Remember, in gear reduction, the drive gear is moving faster. In torque reduction, the driven gear moves faster. This is where we get our overdrives at. Okay, and now instead of the drive gear being smaller than the driven gear, in torque reduction, the drive gear is larger than the driven gear. Okay, this results in an increased speed. In other words, we can have higher highway speeds, but we have a decrease in torque. We no longer multiply torque, we actually get a torque reduction. But what it gives us, since it's an overdrive, is we are able, since the input, the transmission, the engine, is now moving slower than the output, which is your driven gear, which powers the rear wheels. The engine RPM will come down, and then we can get better fuel economy. That's why we have overdrive transmissions. Here's kind of a picture that kind of describes it pretty well. If you look at how these gear ratios work together, if you look in first gear in this setup, we have a gear ratio of 2.5 to 1. And if you look at all these gear ratios, where first gear is 2.5 to 1, second gear is 2 to 1, third gear is 1 to 1, fourth gear, which is overdrive, is 0.8 to 1. You can see as the number gets smaller, we get a higher gear ratio. when the gear ratio number is higher, we get a lower gear ratio. Okay, so the bigger the number, the lower the gear ratio. We figure this one by, if you look in first gear, we have 50 teeth on the driven gear and 20 teeth on the drive gear. So if we divide 50 by 20, we get a gear ratio of 2.5. In other words, the drive gear rotates 2.5 times faster than the driven gear. So every time the drive gear rotates once, and that's the 1 in our ratio, the driven gear rotates 2.5 times. That's our 2.5 to 1 gear ratio. If we move to second gear, where we have 40 teeth on the driven gear and 20 teeth on the drive gear, 40 divided by 20 is 2. So the 2 means that the drive gear is rotating twice, and the 1 means the driven gear rotates once in that same amount of time. So you see how we get our gear ratios. And then we come to our third gear, and this one, which is 1-to-1, which is our direct drive. And again, we'll talk more about direct drive, overdrive, low gears when we get into planetary gear sets. But you can see where both gears are the same size, 20 teeth on each one. So 20 by 20, 20 divided by 20 is 1, so we have the 1-to-1 gear ratio. So the drive gear turns once, which means the driven gear turns once. That's a direct ratio. In our older transmissions before overdrive, this was always our top gear. Even in our first transmission that we talked about, our Hydra-Matic that was in our Oldsmobile, it had 4 speeds, but the top speed was 1-to-1. We did not have an overdrive. And then you can see in our fourth gear where our drive gear is now bigger than our driven gear, and you get 16 divided by 20 is 0.8. In other words, our drive gear turns 0.8 of a turn to every 1 turn of our driven gear, and that gives us our overdrive, to where our drive gear is actually spinning slower than our driven gear. And then reverse, we are able to get reverse because now we put a transfer gear or an idler gear. So if you can tell, look at our top first gear, it shows arrows of the direction of our gears. The drive gear is turning clockwise, which makes our driven gear turn counterclockwise. In reverse, we can get those if we turn our drive gear clockwise. That will actually turn our driven gear clockwise, because now that we have an idler gear, we can get our output gear to move in the opposite direction that it normally would if the drive and the driven gear were meshed together. But when we're figuring gear ratios of, say, reverse, we do not count that idler gear. As you can tell, we still take the 50 teeth of the driven gear divided by the 16 teeth of the drive gear gives us our gear ratio. In this situation, we do not count that idler gear in how we figure our gear ratios. Now that we know how to figure individual gear ratios, like for first or second or third, or if you're talking about a differential, we can also figure overall gear ratios, because we'll have gear ratios in a transmission, and then we have a gear ratio in our differential. Even if we're talking about a transaxle that has the final drive or the gear, the differential in the transmission, it has a separate gear ratio than our transmission. Where a transmission can switch gear ratios, a differential cannot. That's a fixed gear ratio. It does not change. Where in an automatic transmission or even a manual transmission, as we shift gears, we are changing the gear ratio of the vehicle. So an example that I have here, the first gear ratio of an automatic transmission is 2.68 to 1. That would be first gear. Where the rear axle ratio is 3.45 to 1. To get the overall ratio, we would take and multiply the ratio of the transmission by the ratio of the differential. So 2.68 times 3.45 gives us an overall gear ratio of 9.246 to 1. That means we have quite a bit of torque multiplication or gear reduction happening in first gear. And not only through the transmission, but also through the differential. This is needed to get vehicles moving. We need torque multiplication in lower speeds because vehicles are heavy, and we have to get that vehicle moving. It takes more torque and force and power to get the vehicle moving. So we assist that by getting gear reduction, which gives us torque multiplication. Once we get that vehicle moving, highway speeds, then we can have our direct one-to-one or our overdrive, because now we don't need that torque multiplication because the vehicle is already moving. Some different gear ratios. We have our low first gear, intermediate ratios, then a high gear, that's our direct drive. This is what most our vehicles up to through the 1970s used, with like 3-speed transmissions. Okay, if you remember, we did not see overdrive automatic transmission until we got into the late 80s. All right, most our transmissions and transaxles, automatic wise, were the top gear was direct drive. Most of them were 3 speeds up until we got overdrive units in the 80s. Okay, and these were a 4th gear, and like I said before, this was the lower engine RPM at cruising speeds, because once the vehicle is moving, we don't need that gear reduction, we don't need that torque multiplication, so we'll lower the engine RPM while going the same speed, which gives us better fuel economy. Okay, where even our direct drive, where it's 1-to-1, a good way to put this, if we're going 60 miles per hour with a direct drive, say our engine RPM is 2400 RPM. We put an overdrive transmission in it that has a 0.7 to 1 overdrive gear ratio, and that drops our RPM to 2100 RPM. So you can see why that drop of 300 RPM, the engine's not having to work as hard, not having to move as fast, which gives us better fuel economy. Now that we've kind of talked about gear ratios, how to figure gear ratios, what these gear ratios mean, I kind of want to show you examples of gear ratios in a transmission. And how transmissions evolved from even just our 4-speed overdrives to now 10-speed transmissions that we're finding in vehicles. Okay, this example is of what we call a 4R70W. This is a Ford overdrive automatic transmission. This is basically the same transmission as the AOD. If you remember from the history lesson, this was the Ford's first automatic overdrive transmission in, I believe, '89. They went electronic a few years after that and called it an AODE, and then they changed the name of it to a 4R70W. Now they did make some changes to the transmission, like these gear ratios that we see for the 4R70W are not the same gear ratios that we would have seen in the AOD, and the 4R70W is a little stronger transmission, but the internals are essentially the same. How they shift through it are pretty close to being the same as the AOD. So basically, this is the 4-speed overdrive transmission that Ford used for a very, very long time, up into, I think, even the late 2000s. They were using this transmission. As you can see, in most of these, they have a pretty good jump from first gear up to second gear, and then you can see the increments as they're shifting gears. And if you remember from our lesson of when we talked about why we even have multi-speed transmissions, and that was so we could match the engine displacement and output to the desired design of the vehicle. In other words, if we have a big 6,000-pound truck, we need some low gears, we need to get the vehicle moving, we want our power at the lower speed, more torque at lower speed, lower RPM, to get the vehicle moving, because those vehicles are going to be used for pulling stuff. Not only the vehicles are heavy, the stuff they're going to pull is going to be heavy. So we want to adjust our gear ratios. They're going to be a lower gear. In other words, the numbers are going to be higher to give us more torque multiplication. But say if we have a small car, or maybe let's take a sports car that maybe be 3,000 pounds, and the engine's going to run really high RPM because we want to go really fast. We don't need as much torque multiplication at low speeds because it doesn't take a whole lot of as much power to get the vehicle moving because it's light. We're not going to be using a Corvette to pull a horse trailer. So we don't need that gear reduction, that torque multiplication that we need in a bigger truck. So we can change our gear ratios to adjust for that. Well, the whole idea of our multi-speed transmissions is to try and keep that engine in the optimum RPM range to match the design of the vehicle. Well, for the longest time, up until overdrives, it was 2- and 3-speed transmissions. Then when we added overdrive, it was, for the longest time, it was 4 speeds. Then they added a 5th speed and the 6th speed. But now, which is our next example, we have a 10-speed. And this is Ford's 10R80. As you can see, where before we'd have in our 4-speed, we have one low gear, we have an intermediate ratio, a direct drive, and an overdrive. We have a really low gear, even second is lower than our first gear or low gear in our 4R70W. Then we have multiple, if we go third, if we call first and second our low gears, so we'd have essentially 2 low gears. Then third, fourth, fifth, and 6. So 4 intermediate gear ratios. Then we have still 1 direct drive gear ratio. But then you can see 8th, 9th, and 10th is basically 3 overdrive gear ratios. Again, we have a big jump from our first to second, and we have a really low first gear. But now we have much smaller increments between our gear ratios. Now it's much easier with all these speeds to keep our RPM of our engine in its peak operating range. That is why we're adding so many gears to transmissions. It's all about keeping our engine in the peak operating range for performance and fuel economy. Because if we can get better fuel economy, we can get better emissions, which means we make our CAFE standards. Again, if we remember from our engine performance class when we were talking about emissions, everything we're doing on vehicles, yeah, they want to get performance out of them, but everything is centered around getting better fuel economy and making sure we get better emissions. What we're doing with transmissions is the same thing. We're trying to keep that engine in peak operating range so we can get better emissions and better fuel economy. To sum this lesson up, we have many different types of gears in our automatic transmissions. They may be constructed differently, but they all have a similar function. We're transmitting power from a source, like our engine, in our drive gear, and we're transmitting it to our driven gear, which then is our output device, whether we're talking a speed sensor, whether we're talking power to the wheels. They all work similar with each other. We can calculate this transfer torque through gear ratios. In other words, we can calculate what our gear ratios are by counting the number of teeth that are on our different gears that are meshing together. And these different gear ratios give us the different speeds of our transmission. Okay? And as we go through this, our next lesson is going to be on planetary gear sets. But then we're going to get into clutches and bands, and that's where we're going to see, in our planetary gear sets, we're going to see how we use a planetary gear set to get our different gear ratios, and then we're going to talk about in our clutches and bands, first of all, how they work and how they are used with our planetary gear sets to get our different gear ratios.